Okay, in this tutorial we're going to go through an example of what's called the build on surface method. And this is going to be slightly different from what we covered in class. So we need to start with a base surface. In this case, we can either use something from the Lunchbox plugin for Grasshopper. We went over these different kinds of surfaces. But just in case you don't want to use that, there's of course other ways to do it. We can import a surface from Rhino. So here's just a plain surface with control points turned on, and I'm just going to select some of these surfaces, select some of these control points, and move them. So we have a surface to work with. Set this point to 0. Okay, good enough. Wings off. And using the black hexagon surface, let's import this surface. Set one surface. There we go. Okay, the next thing we need to do is the divide surface, divide domain. This object here. And we'll also need an isotrim. Okay. Which will give us division parameters with this object, the divide object here, and the subsurface will actually create those surfaces based on the division parameters. So we'll drag the surface into both. The default here is 10 by 10. We can set this to sliders or panels. Set it to say 5 by 5 for now. Okay. And so now we've got 25 surfaces instead of 1. Now if we were using the Lunchbox plugin, if you're able to install that successfully, you will need the latest version of Grasshopper, but he has a component that does this directly with one component. So it's just more efficient that way. Same thing, this one's at 10 by 10. But for the sake of those of you who don't have Lunchbox installed, we'll just go through this the ordinary way. Okay, now that we have these subsurfaces, next step is to explode them using the brep components command, component here, which will break each surface up into its individual faces, edges, and vertices. So for each surface we'll have one face, 4 edges, and 4 vertices. And in class we used the vertices to create pyramids. Let's do something a little bit different this time. I'm going to take these edges and join them together using join curves. And then find the area, use the area command to find the center point of each of these surfaces. And then I want to scale each of these. Now these are edges joined into closed polycurves. So scale each of those around the center point using scale. The geometry we want to scale is these curves. The center point is here, and we need to graft this center point. See how before we grafted, it was applying to every single, because we had this list of 25 lists of 1 here. and the center points are at one list of 25. So it's kind of cross-multiplying these and giving us these really funny results where it's applying to each center point. So we need to graph this list so that we have 25 different lists. We could also flatten this list and it would have the same effect. Either way is fine. I'm going to graph this one instead. Okay, then we can hide all of this. Okay, and the default scale factor is 0.5. We could change this, so these are now scaled to half the size of the original boundary. Of course we can change this to 0.25, it gets much smaller. We can come back to that. Okay. Now let's move these scaled geometries in a direction perpendicular to the surface itself. And we want to do that using the normal vector. In order to find the normal vector, we need the closest point command. So that's the surface CP, find the closest point on a surface. And the point we want to use are these area centroids. And the surface we want to use, of course, is our base surface from before. Okay, and that's giving us the UV parameter. Using that, we can use the evaluate surface component. And that will give us the normal vector. Okay, and here's the normal vector from the evaluate surface component. So next we want to move the object. We want to move this object along the normal vector. So let's also find a vector amplitude. So we can change that. So the vector is the normal vector. The amplitude we can set at, let's set it at 4 for now. And the geometry that we want to move is this scaled geometry here, and along this now scaled vector. And again, we need to graph this. Alright, so 4 is kind of far, let's just change it back to 1. This is the same as normalizing a vector, putting it at 1. Okay, so let's turn all this off. Right. Okay, so now we have these two types of rectangles, or closed polycurves, the original boundaries of the subdivided surfaces, and these now moved up and scaled down versions of them. So if we just loft these two together, we can create a kind of irregular truncated pyramid. So we drag this, and then holding shift, we need to hold shift, and you see this little plus sign that comes on the end of my cursor. We can squeeze two inputs into one object like that. And so you see that now it's given us these nice four-sided lofts. Now what's important when you use the loft command is that you have data streams that match, and in this case we happen to have matching data streams. And again, you can view that using the parameter viewer, param viewer. So here we have data with 25 branches, and here we have the same. Now imagine that we didn't. What might be helpful sometimes is to use the merge command, and there we can drag both of these in, and if we simplify, and if necessary graft or flatten, and this can always ensure that we have the right kind of data. So now we see we have 50 defined values in 25 lists of 2. So each list contains one big rectangle and one small rectangle. and we could also just drag this into the loft. This is just more of a security check, I guess, on the type of data you're using. Okay, so now that we have our basic geometry set up, let's add a basic attractor system. Okay, I'm going to turn off everything but the lofts, and we're going to add to the Rhino document. I'm going to add, let's say, 2 points, one here and one here. Select those points, double click and make a black hexagon point object, and set multiple points. And you can see that these 2 points are now referenced in the Grasshopper document, that they have these red X's on them. Okay, and then if we do a closest point, we want this one with the black and the one red point on it. And then the points that we're searching from go here, and we want to search from these original area points, these points here. So for each of these 25 points, we want to find the closest of these 2 points and what the distance to the closest point is. Okay. So now we have these distances, and we can see that list of 25 values in units of how close is the closest point. We can remap that into values, say, for let's say the scale factor, and so that we can change what here is a consistent scale factor of 0.25. Of course, we can change that manually, but instead of having a consistent factor here, we can make this a variable that changes based on the proximity to the attractor point. Okay. So we do that again with the remap numbers, and we're going to remap these distance values, and we need a source domain and a target domain. Target domain we can make ourselves. So let's say this is going to be the scale factor. Let's say the smallest scale factor would be 0.1, and the largest scale factor would be 0.5. So that's our target domain. And for our start domain, our source domain, we need to find the list length here. And a sort component. So we're going to sort these values so that they're now in order from the closest to the furthest distance. Then we want to use the list item to find the closest value, which in this case is 2.07, and the furthest value. So we can just copy that, and the list length will tell us item number 25, but actually we want item number 24. That's why this is turned yellow. We can add an expression, I minus 1. So I minus 1, 25 minus 1 is 24, and item number 24 is the largest item in this list, 13.27. We can check that here, 13.27. So our domain is going to be from our source domain is 2.07 to 13.27. Right. So So now we have remapped numbers in the same order. Now these are unsorted, and these are still in an order that is relative to the original geometry here. We have this remapped list, and we can drag that directly into our scale factor. And we'll need to graph that as well. So you can see that closer to the attractor points, the smaller the aperture is. Now we could invert this by switching the 0.1 and 0.5. So we say instead we put 0.5 as the start of the domain. So now they're all at 0.5. And 0.1 as the end of the domain. So now this is just inverted. Okay, and we can select all of this and Control G to make it a group, just so we know that this is these are the objects here that are remapping our data stream. Now we could also just, let's say we want to, instead of making the attractor system apply to the size of the aperture here, maybe we want the attractor system to apply to the length of the offset or the amplitude. So right now everything's at 1. What if we wanted it to go instead from 1 to 4? We could just change, disconnect this. Now they're all at 0.5 again. Let's change them all back to 0.25. And we can make this this domain. So this can now apply to the amplitude, right? Which is now at 1. Let's make this domain from 0.5 to, say instead, 4.0. And we drag that to the amplitude. And we've now got a gradient of how far these are pushed up. The closer they are to a point, the less they're extruded or offset. And of course we can move these points around and the geometry automatically updates. Okay, and then we can just bake our results. And there we go. You can change this to a denser gradient as well, of course. And these are already joined together, so let's just bake. And then we can render or export to Pepakura or whatever. That's all.